Hello friends, my name is Vikas. Today we will do this chapter distribution law. So we start this chapter. It is observed that when a solute is added to a mixture of two immiscible liquids in both of which it dissolves, then it distributes itself between both the liquids in such a way that the ratio of concentration of the solute in both the liquids remains constant at a constant temperature. These observations were made by Berthold and Jungelius by dissolving iodine to a mixture of carbon disulfide and water. Nernst, however, showed that the ratio of concentration is constant only when the solute has same molecular mass in both the solvents, that is, the solute neither undergoes association nor dissociation in both these solvents. The generalization put forward by Nernst is called Nernst distribution law and is started as a solute distribute itself between two non-miscible solvents in contact with each other in such a way that at equilibrium the ratio of the concentration of the solute in the two layers is constant at a given temperature, provided the molecular state of solute is same in both solvents. If a solute X distributes itself between solvent A and B, distribution law is written as concentration of X of solvent A divided by concentration of X in solvent B is equal to C1 divided by C2 is equal to K. The constant K is termed as the partition coefficient or distribution coefficient. Next heading is experimental verification of distribution law. Solution of iodine is in carbon disulfide of different concentrations are shaken with water taken in different bottles. A known volume of each layer CS2 and water is pipetted out and titrated against sodium thiosulfate solution and the concentration of iodine is determined. Similarly, experiment can be done by dissolving succinic acid to a mixture of ether and water. And the results show that the ratio C1 divided by C2 is almost constant. However, hence the distribution law is valid in this case. Conditions for the validity of distribution law: first is constant temperature, second is the two liquids are immiscible or partially miscible, third is the solution are dilute, fourth is the molecular state of solute is same in both the solvents, that is, the solute does undergo association or dissociation in a solvent. These laws are not valid for foam dimers in chloroform. Similarly, the law does not hold the distribution of benzene acid in benzene and water, because benzoic acid exists as dimer. C6H5COOH twice is benzene. Next heading is thermodynamics derivation of this distribution law. The principle underlying the derivation of distribution law from thermodynamic is that in a phase equilibrium established between the two immiscible liquids, the chemical potential of solute must be same in both the phases. Suppose a solute is present in two immiscible solvent A and B in contact with each other. Suppose further that its chemical potential in solvent A is mu A and solvent B is mu B. When two phases are in equilibrium, their chemical potential will be equal to one another. Second heading is modification of distribution law with change in molecular state of solute. Nernst showed that the ratio C1 divided by C2 is constant only when the solute has the same molecular condition in both the liquids. That means that the solute does not undergo association or dissociation in any liquid. However, if any of such change take place in one or both the liquids, then the distribution law get modified. Let us consider in case in which a solute may associate or dissociate or enter into chemical combination with one of the solvents. First is association of the solute in one of the solvents. Let X represents the molecular formula of the solute, let it remain normal in phase, which its concentration is C1. uh, Assume that the solute undergoes association to form molecules Xn in phase 2. Let the C2 be the concentration of solute in this phase. So next heading is application of distribution law. First is, in calculating the solubility of solution in a solvent, the solute added to two immiscible liquids form saturated solution with each liquid. Therefore, the concentration as equilibrium are equal to the solubility of solute in both liquids. C1 divided by C2 is equal to S1 divided by S2 is equal to K. C1 is equal to S1, the solubility of solute in liquid 1. C2 is equal to S2, the solubility of solute in liquid 2. Knowing K and solubility in one of the liquid, its solubility in other liquid can be determined. So next heading is study of association or dissociation of solute. As known above, if a solute associates in one of the solvents in which the concentration is C2 but not in the other in which its concentration is C1, then C1 divided by n root C2 is equal to K. N is a simple number and can be calculated as follows. A, by heat and trial method, the values of C1 and C2 obtained in the experiment are put in the equation. Then putting n is equal to 2, 3, 4 and to infinity, the corresponding values of K are calculated. The number which gives a constant value of K is the correct value of n. B, logarithm method, we have the equation C1 divided by n root C2 is equal to K. C1 is equal to C2 power 1 by n into K. Taking logs on both sides, log C1 is equal to 1 by n log C2 plus log K. For two experimental values C1, C2 and C1 dash, C2 dash, we can write log C1 is equal to 1 by n log C2 plus log K. Log C1 dash is equal to log 1 by n log C2 dash plus log K. On subtracting equation 2 from equation 1, we have n is equal to log C2 minus log C2 dash divided by log C1 minus log C1 dash. Hence n can be calculated. Similarly, when a solute undergo dissociation in one of the solvent in which concentration is C2 but not in the other in which its concentration is C1, then C1 divided by C2 bracket 1 minus alpha bracket close equal to K. Thus, if the degree of dissociation of the solute is known at one concentration, its value at any other concentration can be obtained since K is constant. So next heading is distribution indicator. It is common observation that iodine distributes itself considerably more in carbon disulfide than in water when both the solvents are in contact with each other. Therefore, an extremely dilute solution of iodine in water can be successfully titrated by adding a drop or two of the carbon disulfide. The concentration in the carbon disulfide layer becomes large enough to give a distinct violet color. Next heading is determination of degree of hydrolysis and hydrolysis constant of aniline hydrochloride. Aniline hydrochloride is a salt of weak base aniline and a strong acid HCl. Its degree of hydrolysis is determined as follows. First step is determination of hydrolysis constant. A known mass of aniline hydrochloride is dissolved in dilute hydrochloric acid is known of known molarity. A known volume of benzene is added to it and the mixture is shaken till the equilibrium is attained. On standing, the mixture separates into two layers. The hydrolysis reaction of aniline hydrochloride is The aniline hydrochloride salt will be present in two forms, namely one unhydrolyzed salt, second is hydrolyzed salt. The hydrolyzed constant is given by as Kh is equal to C6H5NH2H3O plus divided by C6H5NH3 plus. A known volume of benzene solution is withdraw and analyze for base and is found to contain aniline. The amount of unhydrolyzed salt, total amount of salt added C6H5NH3Cl minus total amount of free base C6H5NH3, total amount of salt added minus free base in benzene plus free base in water. So our next heading is study of complex ions. The following reactions involving formation of complex ions. Ki plus I2 goes to Ki3. So distribution law has been applied in determining the formula of complex ions I3 minus and Br3 minus. The following examples will illustrate the method. First, a solution of iodine in carbon disulfide is taken with water and distribution coefficient is calculated. Second, a solution of iodine in CS2 of known concentration X is taken with an aqueous solution of Ki of known concentration. Third is after the equilibrium is established between the two layers, the concentration of iodine left in CS2 layer is determined volumetrically by titrating against standard hypo solution. So our next heading is in this process of extraction. So the most important application of distribution law is in the process of extraction in the laboratory as well as in industry. In the laboratory, for instance, it is frequently used for the removal of a dissolved organic substance from aqueous solution with solvents such as benzene, ether, chloroform, carbon tetrachloride, etc. The advantage is taken of the fact that the partition coefficient of the most of the organic compound is very largely in favor of organic solvents. We can derive a general formula which enables the calculation of the amount that is left unextracted after a given number of operations. Let V volume of the solution containing W gram of solute and the repeatedly extracted with V volume of another solvent which is immiscible with the first. Let W1 be the mass of the solute that remains unextracted at the end of the first operation. It is evident that in order to make Wn as small as possible for a given value of Kd, n should be large as possible, but n into V is equal to the total volume of the extracting liquid available, etc. That is, it is constant. Therefore it is better to keep n large and V small rather than the reverse. In other words, the efficiency of extraction increase by increase the number of extraction using only a small amount of extracting solvent each time. For the same reason in the washing precipitates, it is more effective to use a small quantity of other at the time and to repeat the process of number of times. The same principle applies in the desilverization of lead by Parker process. The argentiferous lead melted and heated to 800 degrees Celsius. Molten zinc is then added. Molten lead and a solute which is more soluble in zinc than in lead, the partition coefficient being of the order of 300 to 800 degrees Celsius. Silver therefore uh, passes radially from the heavier lead layer into the lighter zinc layer, which is separated by repeating the process 3 or 4 times. Almost the entering amount of silver passes into the zinc layer. Thank you so much. So our chapter is complete.